Hello guys, welcome to today's session hosted by the Dapp Learning Open Source University. Today's topic is about Risc Zero products. They will introduce their products. It's a kind of workshop. And before we start, please allow me to introduce the Dapp Learning community. So Dapp Learning is a kind of GitHub open source community. It's kind of tutorial, which targets to different levels of developers. We like to help the junior developers with basic skills and understanding about blockchains. And we also provide a big or a friendly platform for all of the developers, including other advanced developers, to communicate and cooperate with each other. So now let's welcome to today's presenter, Angelo. He's a senior engineer from the Risc Zero. So welcome, Angelo. Nice to have you today. Could you give us a short introduction and tell us what you want to teach us or present?
Yeah, absolutely. Thank you for having me. Can I start sharing my screens so that?
Yeah, definitely. Yeah, as always.
All right. Do you guys see everything already?
Mm-hmm. Very nice.
All right. All right. Perfect. All right. I'm Angelo. I work with Risc Zero and currently mainly focusing on Boundless. I'm Italian. I guess it's easy to recognize my accent. I do, as most of the Italian, I do like pizza, pasta, and also zero knowledge.
Spaghetti.
So, right. So actually, my passion for zero knowledge was the main driver that let me, decide to actually join Risc Zero. And as most of the new shiny things, right, you get excited very, very easily, right, with such a, amazing technology. And, ZK is also very along these lines and made a lot of promises, especially when it comes to Web3 and blockchain, right? Because of course, the applicability of ZK technology span across, not only Web3, but also Web2. You can basically use it everywhere. But specifically, when it comes to Web3, in the blockchain, typically, when you have to deal with consensus, you reach consensus most of the case by re-executing, right? All the nodes, right? They need to re-execute, the transaction, whatever computation to basically reach an agreement, and that is basically very expensive. That's why you have these high fees most of the time, right? And so ZK kind of promise that this is gonna be the past, and then you can basically just execute one and verify the proof once and offload the computation off chain. And that also allows for, enabling finally trustless bridging. And we have seen, when we are seeing also, today and, tomorrow, a lot of ecosystem really pushing for ZK adoption. Ethereum, Bitcoin, Solana, but many, many more, right? However, not everything is perfect, right? Especially at the beginning of new technologies, right? So if we look at the current deployment and use of ZK, most of the time you have the prover that is relies on single parties buying the infrastructure to prove. Is also very expensive, right? Because most of the proof system, they have really high requirements when it comes to hardware. Then also from the developer perspective, it's not the easiest technology to understand and integrate yet, right? You basically have very long deployment times, and also especially when it comes to writing specific circuits, that's definitely not a really user-friendly experience. So one of the goals of Risc Zero and specifically Boundless is to fix right? These shortcomings. And basically, Boundless is a universal protocol that its aim is to bring zero knowledge on every chain, right? And so with this in mind, what Boundless is trying to achieve is to basically give you the ability to not only focus on your application deployed on one chain, but you can actually embrace and benefit from a more broader ecosystem by easily deploy your application on any chain, right? And still being able to benefit from zero knowledge magic, right? Also, bringing in this way zero knowledge allows you to basically have boundless execution power, so that you can unlock new application and also save a lot of money in gas fees, right? It's also one of the goals is to be very easy to use, right, and adopt. So that will give you a very low go-to-market time and also decrease the barriers to entry. And with this, we can unlock very nice properties, especially when it comes to, let's think about rollups, right? Having the ability to use ZK to secure their protocol is a good push towards more ZK adoption, right? But that also applies to application and other protocols as well. It is also very high performance. That's important because we are moving in a world also. You have seen a discussion happening on L1 to basically increase the speed at which things get confirmed, and things in general works on Web3, right? So speed is also very important. And again, as I said, it's a universal protocol, so that basically gives you access to an entire set of ecosystem, and you don't have to basically be locked into just one chain or something like that. Now, this presentation is going to be kind of big, right? I try to put so many slides. I think I'll try to skip over some of the details, but the aim of giving you access to this presentation is also because then you can basically stay with something, right? Some point of reference to basically help you understand and maybe get more details about the amazing technologies that we are cooking here at Risc Zero and Boundless, right? So if we think about Boundless as dividing in a set of components, we can think of it as basically the demand side, right? That is basically driven by L1 and 2's protocol, application. And then we have, on the other side, we have the supply, right, the prover, so basically the centralized network that gives you access to the ZK, right? And in the middle, we have this decentralized market that basically does the matchmaking, right, between the two. I'll start by basically give you an overview of how developers can leverage Boundless and also all the frameworks around Boundless, and then we will go to see the others in the rest of the presentation. Right. So just to basically have some common terminology so that we sort of understand what we are talking about, right? If you think about a virtual machine, right? The aim is basically you have a program that you want to run. You also have some inputs that needs to be basically fed into the program, and the virtual machine runs, executes this program, and spits out some output, right? Some result. Now it's very similar when it comes to instead a zero knowledge virtual machine, right? With the only difference that while executing this program with the inputs, not only spits out the output, but also a proof of correct execution, right? That's basically the entire magic of ZKVM, that you can then verify the proof without the need to execute the original computation, right? You can trust the proof. And this applies in a slightly different terminology with the Risc Zero virtual machine, the R0 VM, right? Where the program is basically, we call it a guest code, right? That typically is written in Rust, but we support also other languages. It then gets compiled down to an ELF binary targeting the RISC-V architecture. And then together with the inputs, right? It goes into this R0 VM, which is, our ZK VM. And the result that before, I called output, we call it journal. And the proof, we typically call it receipt, right? So that just to give you an understanding of our terminology. Right, so we were talking about, developers and how, we can write this program. So this is an example taken from the Boundless Foundry template. I'll basically, I wrote some links throughout the entire presentation, and if there is like one thing that I'd like you to basically take with you is those links, because it allows you to basically get even more information and stay up to date with what we are doing. So no worries if you don't read everything here, because all the content is taken from all of those useful resources I'll share in the presentation. Right, so let's get back to our guest code. This is a very short example that the goal is to basically take a number and say whether it is even or not. Basically, it will commit to the result only if the number is even, right? So if we split up the part of the code, you can see that we have an initial phase where we basically read the input, right? And then we decode the number. Then we basically, we check the number. We check whether that number is even. If so, we commit. This is like another terminology. We basically we write the result into the journal. It's just basically committing to the result, right? Everything that you commit is basically going to be part of your output for the journal, right? Then let's say that you have run this program and you basically have your journal, you have your proof, and then you want to consume this into some smart contract, right? Because that's a really, let's say, one of the most useful use case when it comes to integrate ZK and Web3 is to basically use the proofs, right, in your smart contracts. So in this case, we have a set function, right, set method that takes the number, right, the journal in this case, and some call data called seed, which is basically the proof, right, of the receipt. So what it does, it decodes the number, right, and then it verifies that basically the proof is correct. And then only after the successful verification does something else. In this case, it just updates a number, right, to the value of that even number. This is like a very stupid, simple example just to give you an idea of how things are connected together. And here, I was talking to you about these links. Here it's the first set of links where we have the Risc Zero docs, which basically explains all the fundamentals of our ZK R0 VM, right? And then also there are some more related with the Boundless, right? So how to build the program, and also the repository of the Boundless Foundry template that I showed you, right? Now let's go to some example even more interesting, right? So before we saw how we could run Rust code, right? Native Rust code. Now, when we are developing, let's say in EVM, right? One thing that will be super useful will be to interact with Solidity directly, right? And maybe even access the state of whatever chain, right? So for that, we have one of my favorite library and piece of technology we have developed at Risc Zero, which is called Steel, and it's basically a ZK coprocessor, right, for EVM apps. Right? It gives you access to an unbounded computation in a very simple way, right? So Basically, what it does, it pulls state from any EVM compatible chain, right? And then it performs verifiable computation, also across multiple blocks, of chain, and then generates this very, compact proof that is very cheap to verify on chain, so that you can basically have access to a boundless amount of computation now, right? So you can think of your application not anymore with the constraint of how big is the block, how much gas can I actually use in fit in one transaction. So that goes away because you can offload everything off chain and then just bring back on chain the proof and the result. Just to give an example, right? With Steel, you can easily use it to generate the proof for a computation that is equivalent to 30 Ethereum blocks, right? when in terms of gas, right? Which is basically 1.2 billion, right? And you can basically just pay under $10 to generate this proof, right? And then get that verified on chain, which is basically a massive save. Now let's also give you an example, very basic, just to understand the main components here. Right? So this example, it's basically a very a very simple idea to basically increment a counter if only a given address, right, a given account has more than one balance, right, in a given ERC20 contract, right. So this would be implemented by implementing the check, meaning the logic, right, the computation to check that the balance is greater than one on chain. So they are typical standard Ethereum contract. Now with Steel instead, what we can do is that we can strip off the main contract, the on-chain contract, right? The check that we perform on chain, we can offload that, and then we can just bring back the result with the proof, right? So we can decode the result. We can run some checks on the validity of the result, right? And then verify the proof. And only after that, we can, perform our operation. In this case, was increasing the counter, right? And how does this Steel library work? So basically, what we do to make it easy to work is we let the developer just use normal Solidity. Luckily, we have this nice Rust library called Alloy Sol, right? It's a macro that allows you to literally copy and paste, right, Solidity code into your Rust program. It also allows you to read the compile JSON or whatever, interact with the Solidity in a very easy fashion. And then you can basically use all of these to write your guest code, right? So this is an example. You basically read some input, right, first, and then you can basically construct your view code using these bindings that Alloy give you for basically for free. And then you do your checks, right? That you want all the checks all the logic that you want to offload off chain, and then you commit to the final result, to the journal, right? So it's really easy to basically use, and it's super cool because before Steel, the only way to do something like this was to literally go manually find the slot index where the state was stored in a specific contract, and that was very tedious work because you had to use some additional tool to find what the slot index was for a given contract, what variable you wanted to read. So this massively improves the usability of ZK, right, in terms of accessing the state of a contract, right, on EVM chains. And now, behind the scene, the way we can pull this off is we basically, part of the input that goes into the guest are basically coming from a phase that we call pre-flight. which basically what it does, it queries right the code that you want to perform, right, the method, the Solidity function you want to run, calling some RPC nodes. And then together with that, it also calls the ETH get proof, which basically gives you, for each of the the slot index that you have in your state while interacting with this view call, it basically gives you the proof of inclusion, right, against a given block root, right? And so you can gather all this information so that you can provide the guest with a very minimal amount of information that is required for the guest to actually verify that is gonna run this function, right, from a verified state, so that all the all the variables are actually checked already against the root, and that happens all under under the hood. So the developer doesn't need to basically care about this. And so the general idea here is really you have a very heavy computation that you don't wish to run on chain, right? Whether it is because you want to save gas, whether it is because actually you couldn't fit this computation on chain, right? So you can basically use Steel to do that for you, and then you verify the proof, and then you can basically perform some action that is maybe gonna modify the state based on the outcome of that. Right. So this is basically the same increment function I showed you before, just to basically remind you that that is basically the way to do it. Right. I mentioned that when we run Steel, right, when you verify that the state is actually correct, we need a trust anchor, basically, right? Typically is a block root of a given block, right? Now, we still supports two different commitments modes, right? The first one, which is the block hash, which basically uses the block root, right? And then on chain, you compare this with the block hash opcode that gives you access to the latest 256 blocks, which is about 50 minutes, right, in Ethereum, if you consider like every 12 seconds a block, right? And that is basically the time that you have for generating the proof and then consuming it, meaning verifying on chain, right? If you need more time, Steel also support a beacon block root commitment, which instead of using the block hash, it uses the beacon root contract, right? And that extends the time window for basically about a day, right? Now, Steel also supports other features. So we also support Steel history, meaning that you can actually extend even more what you want to prove. So basically, it allows you to query state older than 24 hours, right? So it basically does that automatically. And then one of my favorite things is also the Steel events, which basically, you know that sometimes you might have an application, right, that needs to take some action based on some events generated by some other contract, right? And typically the way you have to do it is to have complex event middleware that basically listen and then, push stuff. So with Steel, instead, you can just use to give to the contract, to some method that you want, the proof that some event has been emitted, right? And that's super powerful and super useful, and it is unlocking already really new use cases in an efficient manner. All right, so these are the resources for Steel. I really recommend you to have a look at those, because Steel is absolutely amazing. And then, what about instead rollouts? How can we actually, use some ZK to improve the life of rollups provider? Right. So we have developed OP Kailua, which is an hybrid zero knowledge for OP rollups. OP stands for optimism, right? The OP stack. And it's a suite of software for upgrading the traditional optimistic rollups to hybrid ZK rollups, right? Which means that you can use a little bit of ZK to improve many of the aspects of our optimistic rollups. Right. So with this, what you're gonna get is basically a set of contracts for dispute, right, in zero knowledge, which is currently only compatible with the OP stack rollups, but we have planned to also support more. And then we also provide you with a CLI tool to automatically migrate rollups to ZK fault proofs. And then also important, state proposer agent, as well as a rollup validator agent, right? Now, this is also very cool because it solves core rollup problems, right? First of all, it saves on proving cost. Then it lowers the participation requirements. So instead of having the need to spend and invest a lot of money to set up proving infrastructure, OP Kailua can just use decentralized proving markets, right? So you don't have to basically put that initial investment. And it also reduces existing rollup collateral costs, which are one of the things that I dislike the most about the traditional optimistic rollup. So instead of having a linear being linear in the number of proposal challenges, it's basically constant. Oh, that's really cool. I also share some resources here. I highly recommend the Kailua book because Kailua is basically in a very active development phase. So the reference that is the more up to date with the current design, you can find it there, right? And of course the repository. And we also have a quick start on the Boundless documentation on how to basically use it. Then we also have something about proving Ethereum blocks, right? That's basically, I think, I would call it the father of Kailua. It came before, right? It's called Zeth, and it's basically an execution layer block prover, right, for both Ethereum and optimism. And with that, you basically have a way to prove that a given sequence of block is valid by applying the given list of transactions starting from a parent block. And you don't need to rely on the validator or a sync committee because, of course, everything happens within the ZK VM, right? So, well, the operation that happens while verifying a block are, you verify all the transaction signature, you verify the account and the storage state against, the parent block. And then you apply all the transaction, you pay the block reward, and finally you update the state root, right? And by using this, you can obtain a ZK proof of a valid block execution, right? Again, here you can find the repo, and also we have a Zeth-based order generator in our Boundless market that basically every now and then it submits an order for proving either a block or a set of blocks. Right. So now we talk about the market, the decentralized market of Boundless. So this diagram is very useful to understand, to have an overview of how this decentralized market works. So basically, you have, the application, the request of, let's say, side of things that needs to have some proof requests to be fulfilled, right? Might be, coming from a Zeth block that wants to generate a proof to validate a block, or it might be a rollup, or it might be your application, or it might be something else. It doesn't really matter. And the request submission can happen both on-chain, but also off-chain if you want to save in more gas. Of course, if you send it off-chain, you have less guarantees about data availability, but it's your choice. And then the market is basically based on a reverse Dutch auction, which means that the request contains, some pricing there, right? Some offer. That then the prover, right? Which is part of, all of this is open and decentralized, so anybody can actually, go there and listen to new proof request submission, and then can also judge whether this is a profitable request, right? If the price is okay, if if the program can actually be executed, right? So there is also the option, since it's a reverse Dutch auction, for the prover to basically acquire the right to be the only prover to be able to fulfill this request for a given period of time, right? And in order to acquire this, the prover also, of course, needs to basically put some collateral, right? So that give the requester some guarantees that the proof will be fulfilled, right? So if everything goes well, the prover will generate the proof and then submit the proof and the results to the market. And the market will verify that everything is correct, and then we'll settle, right? We'll basically transfer the fee, right, to the prover. And then again, the original requester can consume this proof by using it in its application or whatever it needs to be consumed. And yeah, so basically that's the idea of the boundless market. Now it's super nice because it gives you really nice properties. So it guarantees proof delivery, and of course, assuming that the pricing and all the parameters are correctly set. It is also you have some guarantees about getting the best latency and price because of the reverse Dutch auction. So that means that the first prover that promise to fulfill is also the one that will basically give you the best price, because the price goes up over time, right, from the minimum to the maximum price. There is no redundant work in this way because you have this lock-in mechanism that basically allows openly each prover to acquire the right to be the only one fulfilling. So there is no race, but there is also an option to have that open. There is no single point of failure because it's a decentralized network, and those are really nice properties. So if we look at the interface for submitting a request in the market, we can see that we have the proof request, and then we have the signature, right, of the requester. So basically signing that this request is legit, right? And the request is basically composed by some information. Of course, we have the identifier. We have some of the requirements that basically specify some constraint that the output, right, should contain. The image, the URL of the program, basically the image URL, the input that needs to be run against this program, and then also the offer. Now, I will show you a little bit more details about the offer because it's interesting to understand these, to also understand better how the market and the reverse Dutch auction works, right? So we have a minimum and maximum price that is basically the lowest and highest price the requester is willing to pay. Then we have a timestamp defining when the bid is going to start, right? From that moment, we define also a length of ramp-up period, which is basically this defines how fast the price will go from the minimum price to the maximum price, right? And then we have a timeout, which express basically for how long this request is going to basically still be considered alive, right? And then we have a lock timeout, which is instead the time given to the prover that wishes to acquire the rights to be the only one, right, enabled to fulfill the request. And if the prover doesn't respect this timeout, it gets slashed of the collateral that instead is defining the lock stake, right? We have an indexer of the boundless market, and one of the stats that basically you can have access to is also the average price per mega cycle, so that you can have a more a better understanding of how to price your request. Then we also provide obviously a Boundless SDK that basically is a bunch of utilities function to help you construct and interact with the construct request and interact with the market. Right. In this case, we show how to build a client, right? Specifying all the the addresses for the various contracts of the market and the private key and what the RPC URL you wish to use. And then the same SDK, the same client has functionality to help you with uploading the program, right? We support S3, we support IPFS. In general, any URL is also good. And then same things for the input, right? You need to basically find a way for the prover, since this is a decentralized network, to have access to the program and the input that you need to you want them to run. We also have a way for this to work in a more private fashion with the leveraging on AWS, right? So that only the prover that have access, right, to these links of S3, they can actually have access to the program and the input, so you can basically have some more privacy in this way. Then, this is just an example to show how you could use the R0 VM tool to know more about your program. In this case, we basically run the execution, which is basically just running the program without actually proving it. And this gives you access to some useful information, such as how big is your program in terms of cycle, right? In terms basically how expensive will be to prove, right? As well as the journal, right? So you can use these to both ensure that your program is actually correct, how much you should basically price this request, and also define some requirements regarding your specific journal. And then you have your builder for the proof request, so you can basically create easily the proof request that you can then submit to the Boundless market. Again, you can submit a request both on chain or off chain, right? You have different guarantees whether you decide to go off chain, but of course you're gonna save some gas. Then you want to maybe wait, right, for the request to be fulfilled. So we have both blocking and non-blocking, right, methods for this. But basically the goal is once you get back the proof and the journal and basically the receipt, right, you can consume it and basically fed into your application. We also have, I haven't put the slide here, but we also have a detail in the request requirements that is actually gonna specify you a callback, so that the consumption of the proof is actually going to be made directly by the market itself, right? So the request doesn't need to even use the proof, because it will all be part of the proof request lifecycle. And going back to and trying to connect, like the example that we saw before about the even number, right? Here, the idea will be you create a proof request, right, to prove whether X is even, right? And then you can call the wait for request fulfillment, so that you get back the journal and see, and then you can use the sol macro to create your instance of the even number contract and call the set function with using the journal and the proof that you got from Boundless. So basically, this is to make the circle, right? So that means that the set function will verify the proof, and the verify call will revert if the proof is invalid, which will not happen, because otherwise, in general, what you get back from the market is only valid proof, because they have been verified already. And then your program can basically do whatever the program was supposed to do, right? Here are also really nice links. Maybe I can actually, let me see if I can. So we have we have some tutorials here. So basically, this is the callbacks that I was mentioning, so that automatically the request, also the fulfillment of the proof, will also call some method that you want, right? We have a decentralized way so that also smart contract can be requested, right? We also have a way to specify the type of the proof that we want to get back, either a cheap, proof of inclusion, or maybe we want the original Grow 16 because we want to use it somewhere else. We also have proof composition support, meaning that you can prove first a program, and then you can basically use the proof of this program to prove another program, right? So that you can basically build in composing proof together to prove something else, right? We also have a CLI to interact with Boundless, but what I wanted to show you now is actually, yes, this other page where at the bottom we have the link to the indexer, which is basically something like this, right? Where you basically see in our current testnet some orders, right, that have been submitted either off-chain or on-chain, their current status, whether they are fulfilled, locked, or just submitted, right? And then you also have, some other information. If we click to an order, you basically get some more information. You can also have more details about that, about the offer and everything. And we also have some stats page where you can basically see how many orders have been fulfilled. I think somebody raised a hand.
Yeah. I just want to let you know there's a question from Victor. You can check in the chat box. What's the requirements of running a prover? The minimum recommended configuration.
Yeah, sure. I'll get there in a few seconds. Thank you for the question. Okay. Right, so now it comes to provers, right? So we already have like a very good set of provers that they have experience securing and mining also billions. So they have experience in bringing accelerated hardware, and some example on Pool, TK Pool, P2P, Rockaway. But it's an open network, so anybody can actually go and participate. We provide a set of software that compose the proving stack. Basically, you have two pieces of software. It's Bento, which is this multi-GPU, multi-machine prover, right? That is open source. You can run it. And we also have the broker, which is instead a piece of software that basically sits in between the market and Bento, right? So it's the one responsible for evaluating requests, bidding on requests, issuing proving requests, and so on and so forth, right? And when it comes to the requirements, we do recommend this type of requirements. They are not crazy. It's let's say, commodity hardware. However, that doesn't mean that you cannot basically participate as a prover with way less hardware, right? This is just to remind that the expectation of being profitable, of course, needs to be set according to the capacity that you bring into the network, right? So that means that if you come with just let's say a GPU, right, and even just a laptop, you can participate, right, to the market, but you might be slower, right? So that means that you will be able to accept less orders, right, with respect, for instance, to some bigger prover, right? So that's basically the point. Is you can participate with any hardware. But when it comes to be profitable in this competitive market, then of course, it makes a difference. The amount, the power that you bring in, right? So that's basically the point. And then the other requirements are really just Ubuntu. Currently, we support only that. Docker Compose, everything is done via Docker, so it's not really that difficult to run a prover. And in the current phase, we also have a requirement for the stake collateral. It's basically a toy token. It's called HP, stands for health points, the idea, right? So if you wish to participate, just fill out that form link in the presentation, and we'll give you access with some HP tokens. So completely it doesn't have value, right? Currently, it's just a toy token, just to make that clear. Right, so these are other important resources for the developers side of things. We plan to, have mainnet in Q2, so really welcome to come with us, and that's basically it. I'll go back to the maybe stop sharing for a second so that I can see. Okay, now I see you all, right?
We also have a friend asking what's a commitment, but I don't get which slides.
Yeah, I think it's for the still library, right? So basically, a commitment is imagine that you want to read some storage slot on some contract, right? Let's say, and that value is only, let's say, verifiable by using a proof of inclusion, right? Using the ETH get proof that basically attests that is the value, correct value, assuming that the block root is whatever block, right? Let's say block number 10, right? So commitment means that you are committing to that block number, right? And so that you basically have applied the verification against that block, so that once you basically verify that on chain, you can make sure that that block is actually a valid block. Is this true? It's not just a fork or some other shenanigans block. So that is a commitment, right? And that's a type of commitment using the block root. But there are also other type of commitment using maybe the beacon root.
Yeah. Okay. Any questions?
Hello, I have a question. Can I use Steel to get get an API from Web2 website? Then can I generate proof for it?
So your question is if you can use Steel to generate a proof for a Web2 API, right? Response.
Yeah.
Okay, so no, meaning that Steel is basically meant to run EVM. So basically, literally just say something about the state of a given EVM chain, right? So that is the short answer. The better answer will be that a technique similar to Steel could be used, right? It could be built to prove, the correctness of the response of a given API in the Web2. But that is mainly gonna be focused on how to prove that a TLS session, right? HTTPS session is actually, correct. That is kind of tricky for various reasons. The main reason is that in order to be easy to achieve such a primitive, the TLS should be slightly modified, or at least use in a subset of what's available, right? Because TLS can be upgraded to different key mechanism. So there are some caveats about securing let's say proving the exchange, but there are also already a few solutions out there. I don't remember on the tip of my tongue the names of these solutions, but they are. If you look ZK TLS, yeah, something along those lines. You can definitely have a look at that. We are also interested in exploring a little bit more this. But yeah, definitely it's a super interesting topic.
Yeah, you are right. ZK-TLS may be the solution. So I wonder whether I can use Risc Zero for ZK TLS?
No, absolutely. You can use Risc Zero for basically proving right what ZK TLS implements. The problem with ZK TLS though is that there are still some assumptions, right, that might be good for your use case or might not be good enough, right? So have a closer look at what ZK TLS is able to provide, right? Because it's not, I personally, I don't think it's still like the, ideal solution to this use case, unless of course, there are some assumptions that you are okay with it.
Oh, okay, yeah, thank you.
Any other questions? You can type in the chat box or just open your microphone.
I do have a question. Is it possible to share the presentation with all the attendees so that they can basically have access to the links?
Oh yeah, definitely. Yeah, we will
that
the
would be
links
great.
to the community chat or something.
Thank you.
Yeah, they can get from our official website. Yeah.
I think I got a question from the community. It's a very generic question. It's what types of teams you think will get the benefit from the Boundless? What type of teams? Like the team working on the Ethereum, the team working on the ZK Sync, or very generic one.
The point is, I'm not sure, right? But definitely, one of the goal is to be, as universal as possible for us, because we do believe that, ZK shouldn't wear any flag, right? It should really be applicable to any sector, any chain. I do believe that the way and the pace at which ZK will be adopted will be very dynamic in the near future, meaning that we will see a massive increase of demand for ZK, especially because some projects like Risc Zero, but also others that are really pushing and improving the UX experience for enabling this. And then also, we have to see how the core protocols will evolve, right? They might also think to actually embed ZK within their, their natively protocol. So that will also play a role. And then, I guess definitely the Ethereum ecosystem is well suited, especially because it's expensive, right, to run stuff on Ethereum. So everything that can be offloaded is good. But I saw a lot of interest also from Solana ecosystem, even though there is already kind of faster and cheap. I think it's not only saving us; it's also unlocking application that still cannot fit in one block, right, on a few transactions. So that is also important.
Okay. Thanks for your answers. Yeah, thanks a lot. Any other questions?
Yeah, I have another question. Can you briefly introduce the difference between Risc Zero and SP1? Yeah.
Sure. I mean, absolutely. So Risc Zero kind of created the first ZKVM based on Risc 5, and at the time everybody were kind of surprised why choosing Risc 5 over some other architecture, right? But and it was also the period where it was very common finding teams developing specialized circuit EVM, right, rather than ZK VM. So we kind of show to the world that can be done really well. So then obviously other capable team kind of like the idea and start to base their work off of it. So we're really happy about it. And now I guess it's not only Risc Zero, right? Also SP they provide a really good good solution. We do differ mainly in the way we approach security, meaning that if you really care about security, and if you look at the the Bitcoin space, I think we are top notch. There is literally no comparison. I mean, no game with that. When it comes to speed, it's like a topic that has been I get it, but the development in the space is going so fast that by this time next year, nobody will ever talk again about performance, because things will be so fast that nobody really cares about the the minimal differences. So it can happen that 1 week Risc Zero is faster doing this type of computation. Another week SP is faster doing this other. There is also other ZK that are faster. It's like moving very, 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 very fast, right? And things are changing. So I would not put the current performance to be the only deciding factor to choose a technology. Rather, I would look at how the project is evolving. Security and decentralization and all of these things. So yeah.
All right, I see. Okay, thank you.
Any other questions before we end? Okay, I think that's it. Yeah, thanks, Angelo. Thanks for your excellent and detailed presentations. I think we all get the basic understanding or intensive knowledge about leaking sync and Boundless. Thanks for your presentation again, and thanks for all of attendees to show up in the Dapp Learning. Yeah, we will see you next time.
Thank you. Bye.
Thank you, guys. Have a nice day. Bye-bye.